Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us into 100 sleepy facts about clouds, where drifting shapes reveal hidden stories about water, wind, light, and the changing sky. We will explore how clouds form, why they take such different shapes, and how they help carry Earth's water through the air. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. In the quiet sky, clouds begin when invisible water vapor turns into tiny droplets or ice crystals. Water is always moving through the air, even when the sky looks perfectly clear. Warm air can hold more water vapor than cool air. So when air rises and cools, some of that vapor can no longer remain invisible. It gathers into countless small particles, each one too tiny to see alone. Together, they scatter sunlight and form the soft white or grey shapes we call clouds. This simple change from vapor to liquid or ice is called condensation. It happens quietly above hills, oceans, forests, cities, and open fields. A cloud is not a solid object, but a floating collection of water in one of its gentlest forms. Most cloud droplets need tiny particles in the air before they can form. These particles are called cloud condensation nuclei, and they may be bits of sea salt, dust, smoke, pollen, or other natural material. Water vapor gathers around them because it is easier to form a droplet on a surface than in completely empty air. Over the ocean, sea spray can send salt into the atmosphere, helping low clouds appear above the waves. Over land, wind can lift fine dust from soil or dry ground. These particles are extremely small, yet they help shape the visible sky. Without them, cloud formation would be much harder. A cloud may look pure and simple, but it often begins around specks so small they drift unseen. The dew point helps reveal when air is ready to form cloud. Dew point is the temperature to which air must cool for its water vapor to begin condensing, if the amount of moisture stays the same. When air temperature and dew point are close together, the air is nearly saturated, meaning it is close to forming droplets. This is why fog, low cloud, or dew can appear when nighttime cooling brings air down to its dew point. In rising air, cooling toward the dew point can create a cloud base above the ground. The idea sounds technical, but it is simply a measure of moisture waiting to become visible. Dew point connects a clear sky, a misty morning, and the underside of a cloud. It marks the quiet threshold where vapor becomes water. Adiabatic cooling helps rising air form clouds without needing to lose heat to the outside. When a parcel of air rises, it enters regions of lower pressure. The parcel expands in response, and that expansion causes its temperature to drop. This cooling can happen even if the air is not directly touching a colder surface. If the rising air cools enough to reach saturation, water vapor begins to condense into droplets or ice crystals. This process is central to many cloud types, from small fair weather cumulus to broad sheets lifted along weather fronts. The word adiabatic may sound complex, but the picture is simple. Air rises, pressure falls, air expands, and cooling follows. Clouds often appear because the atmosphere gives rising air more room, and that extra room quietly lowers its temperature. Rising air is one of the main reasons clouds appear in the sky. Air near the ground can warm when sunlight heats land or water below it. As that air becomes warmer, it becomes lighter than the cooler air around it, and it begins to rise. Higher in the atmosphere, the pressure is lower, so the rising air expands and cools. When it cools enough, its water vapor begins to condense into droplets or ice crystals. This is why clouds often grow above warm ground on sunny days, especially in the afternoon. The process is gentle but powerful, lifting invisible moisture into visible form. Each soft cloud is a sign that air has traveled upward and changed as it rose. Mountains often create clouds by forcing air to climb. When wind meets a mountain slope, it cannot pass straight through the rock, so it is pushed upward along the rising land. As the air climbs, it expands and cools, and any moisture inside it may condense into a cloud. This is why mountain peaks can wear pale caps of cloud, even when the lower valleys remain clear. On the windward side, where the air first rises, clouds and rain are more likely. On the far side, the air often sinks and becomes drier. This can create a rain shadow, where the landscape is much less moist. A quiet cloud resting on a ridge can reveal the hidden movement of wind over stone. Along weather fronts, clouds can form when two air masses meet and one is lifted over the other. A warm air mass and a cool air mass do not mix instantly because they have different densities. The warmer air is usually forced to rise above the cooler, heavier air. As the warm air rises, it cools, and clouds may spread across the sky. This process often happens along weather fronts, which are broad boundaries between different kinds of air. A gentle, warm front can bring wide sheets of cloud that arrive slowly and cover the sky for many hours. A cold front can lift warm air more sharply, sometimes building taller clouds. In either case, clouds show where great bodies of air are quietly meeting. Flat cloud bases often appear because condensation begins at a shared height. As warm, moist air rises, it cools steadily. When it reaches the level where the air is cool enough for water vapor to condense, tiny droplets begin to form. Many rising columns of air in the same area can reach that level at about the same height, creating a cloud base that looks almost like a straight line. Above the base, the cloud can rise in rounded shapes because the air continues moving upward in uneven currents. This is especially clear in cumulus clouds, where the bottoms look level, but the tops are lumpy and alive. A flat cloud base is a visible mark of temperature and moisture meeting in balance. Color in a cloud depends on how water, droplets, and ice crystals scatter light. Thin clouds often appear bright white because their tiny particles scatter sunlight in many directions, sending plenty of light toward our eyes. Thicker clouds can look gray because less light passes all the way through them. The droplets inside may still be clear, but the cloud as a whole blocks and scatters sunlight so strongly that its underside becomes shaded. A cloud's color can change with the time of day, the thickness of the cloud, and the angle of the sun. At sunrise or sunset, low sunlight can turn clouds gold, pink, or red. The colors come from light traveling through the atmosphere before reaching the cloud. Although they seem weightless, clouds are not truly weightless. A typical cloud can contain a large amount of water spread through millions or billions of tiny droplets. The reason it stays in the air is that each droplet is extremely small, and the surrounding air currents help hold it aloft. Falling through air is slow for such tiny particles, especially when rising motions inside the cloud push upward. A cloud is less like a suspended lake and more like a very wide mist spread across a large volume of air. The water is real, but it is finely divided. This is why a cloud can drift above us without falling all at once. while still carrying enough moisture to one day become rain. Movement in clouds comes from the movement of the air around them. A cloud does not usually travel like a solid object being pushed across the sky. Instead, it is made of droplets or crystals that are constantly forming, evaporating, and reforming within moving air. Winds at different heights can carry clouds in different directions, which is why high wisps may drift one way while lower clouds slide another. A cloud's edges can fade where droplets evaporate, while new parts form where moist air continues to cool. This can make a cloud seem to change shape as it moves. Watching clouds is really watching wind made visible. Their motion reveals the atmosphere's quiet flow above the ground. As part of the water cycle, clouds carry water through the atmosphere. Water evaporates from oceans, lakes, rivers, soils, and plants, becoming invisible vapor in the air. When that vapor cools and condenses, clouds form. Some cloud water returns to the surface as rain, snow, sleet, or hail, while some evaporates again before ever reaching the ground. This movement helps move fresh water from oceans to land, where it can feed rivers, forests, fields, and underground stores. Clouds do not create water from nothing. They gather, transport, and release water that is already moving through Earth's connected systems. A cloud is one quiet stage in a journey that may pass through sea, sky, soil, and living things. The shape of a cloud can reveal the stability of the air around it. When the atmosphere is stable, rising air tends to slow down and spread out, often forming flatter layers of cloud. When the atmosphere is unstable, rising air can keep climbing, building taller and more rounded clouds. This is why some skies look calm and layered, while others grow into high towers. Stability depends on how temperature changes with height and how much moisture is present. People who study weather can read cloud shapes as signs of invisible conditions. A smooth sheet of cloud suggests one kind of atmosphere, while a bubbling cumulus field suggests another. The sky shape is a quiet display of the air's structure. Temperature inversions can trap low clouds beneath warmer air. Normally, air tends to become cooler with height in the lower atmosphere. During an inversion, a layer of warmer air lies above cooler air near the surface. This warmer layer acts like a lid, making it harder for the lower air to rise and mix upward. If the trapped lower air is moist, stratus clouds or fog can persist for hours, or even longer in some regions. Valleys, coastal areas, and winter landscapes often experience this kind of low cloudiness. The sky may stay grey below while higher mountains or hills rise into sunshine above the inversion. A low cloud deck under an inversion shows how a change in vertical temperature structure can shape the feeling and light of an entire day. A stable layer in the atmosphere can limit cloud tops. When rising cloudy air meets a layer where the surrounding air resists upward motion, the cloud may spread sideways rather than continue growing. This is common in stratocumulus decks, where cloud tops can appear fairly even across a wide area. The stable layer works like a gentle ceiling, not a solid barrier, but strong enough to organize the cloud shape. Below it, moist air can keep forming droplets. Above it, drier or warmer air may gently prevent further growth. This helps explain why some cloud fields look neatly flattened at the top edge. Their shape is not accidental. It records the point where rising motion weakens and horizontal spreading becomes easier than climbing into the clear air above. A cloud edge fades when droplets evaporate back into invisible vapor. A cloud does not usually have a hard border. even when it looks sharply outlined from the ground. Along its edges, drier air may mix with cloudy air, causing tiny droplets to shrink and disappear. At the same time, new droplets may form inside the cloud, where moist air is still cooling. This means the cloud is always being renewed in some places and erased in others. Its shape is less like a carved object and more like a balance between forming and fading. Wind, sunlight, humidity, and temperature all help decide how quickly the edges soften. Watching a cloud dissolve is watching water return to a hidden state. Nothing has vanished from the atmosphere. It has simply become too small and spread out for the eye to see. Entrainment happens when clear surrounding air mixes into a cloud. As a cloud grows, especially a cumulus cloud, it does not remain perfectly separate from the air around it. Small swirls and turbulent motions pull drier or cooler air into the cloud's edges. This mixing can change the cloud's temperature, humidity, and ability to keep growing. If the entrained air is dry, some droplets may evaporate, weakening the cloud. If the cloud has strong rising motion, it may keep building despite the mixing. Entrainment helps explain why cloud tops can look ragged, why some small cumulus clouds disappear quickly, and why cloud growth is difficult to predict exactly. A cloud is never sealed away from its environment. It is always exchanging air with the invisible space around it, changing gently from the outside inward. The modern cloud vocabulary began with Luke Howard in the early 19th century. He was an English observer who proposed Latin-based names for common forms such as cirrus, cumulus, and stratus, giving people a shared language for shapes that had always changed from moment to moment. Later, meteorologists expanded and refined the system, but the basic idea remains familiar today. The names often combine roots that describe shape, height, and precipitation. Cirrus suggests wispy strands, stratus suggests layers, cumulus suggests heaps, alto points to middle-level clouds, cirro often refers to high ice clouds, and nimbus marks a connection with precipitation. The system helps people read the sky without needing a separate name for every passing variation. A cloud name is a small description folded into one word, turning a changing shape into something that can be noticed, remembered, and compared with distant skies, far away. A simple height system groups clouds because the atmosphere changes with altitude. Low clouds usually form close to Earth's surface, where temperatures are often warmer and droplets are more likely to be liquid. Middle clouds float higher, where the air is colder, and their water may be partly frozen. High clouds form in the cold upper troposphere, where they are often made mostly of ice crystals. These height groups help people understand what kind of weather a cloud may bring. A low grey sheet can suggest steady dampness, while a high, thin veil may signal changing conditions far away. The names may sound formal, but they are simply a way of reading the sky in layers. Cirrus clouds are high, thin clouds made mostly of ice crystals. They often look like pale feathers, fine brushstrokes, or delicate strands stretched across the blue. Their name comes from a word meaning a curl of hair, which suits their wispy shape. Cirrus clouds form so high that the air around them is very cold, even on a warm day at the ground. Strong winds at those heights can pull the ice crystals into long, graceful trails. These clouds usually do not bring rain to the surface by themselves, because they are too thin and too high. Yet they can hint that moist air is moving overhead. Cirrus clouds give the sky a quiet, distant texture. Cumulus clouds are the puffy clouds that often look like soft hills or cotton piles. They usually form when warm air rises from the ground and cools into visible droplets. Their bases can appear fairly flat because condensation begins at a certain level, where rising air reaches the right temperature. Above that level, the cloud may billow upward into rounded towers and domes. Small cumulus clouds are often signs of fair weather, especially when they remain low and separate. They can drift slowly across a bright sky, changing shape as air rises through them and evaporates around their edges. A cumulus cloud is always forming and fading at the same time, even when it appears calm and still. Stratus clouds spread across the sky in low, even layers. They often look like a pale grey blanket, softening sunlight and reducing shadows on the ground. These clouds form when moist air is lifted gently, or when a cool layer of air allows moisture to condense near the surface. Stratus clouds may bring mist, drizzle, or a quiet damp feeling, rather than heavy rain. They can make the sky feel lower, as if the atmosphere has settled close to rooftops, trees, and fields. Unlike puffy cumulus clouds, stratus clouds have fewer sharp edges and less dramatic shape. Their beauty is subtle. They turn the sky into a smooth, muted ceiling of water droplets. Fog is a cloud that forms close to the ground. It is made of tiny droplets suspended in the air, just like many other clouds, but it touches the landscape instead of floating high above it. Fog often appears when air near the surface cools enough for water vapor to condense. This can happen on calm nights, near rivers, over damp fields, or along coasts where moist air meets cooler water or land. Fog can soften distance and make familiar places look quiet and unfamiliar. Trees, buildings, and hills may fade into pale layers. Although it seems different from a cloud overhead, fog is part of the same family. It is the sky gently resting at human height. Altostratus clouds often cover the sky with a smooth grey or bluish sheet. They form in the middle levels of the atmosphere, usually when a broad layer of moist air is lifted gently over a large region. The sun may still be visible through thinner altostratus, but it often looks pale and blurred, like a lamp behind frosted glass. These clouds are usually thicker than high cirrostratus clouds, yet less broken and textured than altocumulus. They can appear before steady rain or snow, especially when a warm front is approaching. Their quiet spread across the sky can last for many hours, gradually dimming the landscape without sudden change. Altostratus clouds show how weather can arrive slowly, not as a sharp event, but as a wide, even layer of moisture settling into place above the earth. Altocumulus clouds appear as rounded patches or rolls in the middle sky. They are often white or grey, with soft shading that gives them a quilted or rippled look. These clouds are usually made of water droplets, though ice crystals may be present when the air is cold enough. Their small rounded shapes can form when gentle waves or patches of rising air move through a moist layer. Altocumulus clouds sometimes appear in groups that seem neatly arranged, as if the sky has been lightly patterned. They may signal changes in the atmosphere, especially when they appear on a warm, humid morning. Their meaning depends on the larger weather setting, not just their shape alone. As a sight, altocumulus clouds are a calm reminder that even the middle air can hold fine structure and rhythm. Stratocumulus clouds form broad, low layers with soft lumps and breaks. They often look like a sky filled with rounded grey patches, with brighter spaces where sunlight slips through. These clouds are common over oceans and cooler land areas, especially when the lower atmosphere is moist but not strongly rising. stratocumulus may bring a little drizzle, but they often pass without heavy precipitation. Their bases are usually low, which can make the sky feel close without becoming fully overcast. Unlike smooth stratus, stratocumulus has texture. Unlike taller cumulus, it usually spreads sideways more than it grows upward. This makes it one of the most familiar cloud types in everyday weather. It gives the sky a quiet, dappled ceiling, changing slowly as wind moves through the lower air. Its broad patches can cover many kilometers while still leaving small windows of light. Nimbus clouds are clouds linked with falling precipitation. The word nimbus is often connected with rain, and it appears in names such as nimbostratus and cumulonimbus. Nimbostratus clouds are broad, thick layers that can bring steady rain or snow over a wide area. They often cover the whole sky, making it hard to see where one part of the cloud begins or ends. Cumulonimbus clouds are much taller and more powerful, with rising air that can carry moisture high into colder levels of the atmosphere. Not every grey cloud is a rain cloud, but nimbus clouds contain enough water or ice for drops or flakes to grow heavy and fall. They remind us that clouds are part of Earth's moving water cycle. Cumulonimbus clouds are towering clouds built by strong rising air. They begin as growing cumulus clouds, but when the air is very moist and unstable, they can climb high into the troposphere. Inside, powerful updrafts carry droplets and ice crystals upward, while other regions allow precipitation to fall. The cloud can stretch from warm lower air into very cold upper levels, so it may contain liquid droplets, supercooled water, ice crystals, snow pellets, and raindrops all at once. Its height gives it a dramatic structure, but its basic process is still the same quiet physics of rising air and cooling moisture. Cumulonimbus clouds are important rain producers in many regions. They show how a small upward current near the surface can grow into one of the atmosphere's largest visible forms. The flat anvil top of a cumulonimbus cloud forms when rising air reaches a stable upper layer. As the cloud grows upward, its strong updraft pushes moisture high into colder air. Near the top of the troposphere, the surrounding air often becomes more resistant to vertical motion. The rising cloud can no longer climb easily, so it spreads outward beneath this boundary. Strong high-altitude winds may then stretch the top into a broad, flat plume. From far away, this can give the cloud the shape of a great white tower with a smooth lid or fan. The anvil is usually made mostly of ice crystals because the air at that height is very cold. It is a visible sign that a cloud has reached the upper limit of ordinary weather. Several cloud layers can form in the same sky at the same time. It is common to see low cumulus drifting beneath a higher veil of cirrus, or a middle layer of altostratus beneath thin ice clouds. Each layer belongs to a different part of the atmosphere, with its own temperature, humidity, and wind. Because winds can vary strongly with height, the layers may move in different directions or at different speeds. This layered motion can make the sky feel deep, like a transparent space rather than a flat ceiling. Multi-layer cloud scenes often appear before broad weather changes, when moisture is arriving at several levels. Seeing clouds at different heights is a reminder that the atmosphere is not one simple sheet. It is a stack of moving layers, each with its own quiet weather. Mammatus clouds are pouch-like shapes that can hang from the underside of a cloud layer. They often appear as rounded pockets, soft and uneven, with light and shadow giving them a sculpted look. Mammatus can form when sinking air carries cooler, denser cloud material downward into clearer air below. As the pockets descend, they slowly change and fade. They are often seen beneath the spreading tops of large clouds, including cumulonimbus anvils, but they can appear with other cloud layers too. Their shape may look unusual, yet they are simply another sign of air moving in small, organized ways. Mammatus clouds do not fall from the sky as solid objects. They are patterns of droplets or ice crystals shaped by gentle downward motion and the slow mixing of cloudy and clear air. Lenticular clouds form when air flows in waves over mountains or hills. These clouds often look smooth, lens-shaped, or even like stacked saucers, resting in place while wind passes through them. The cloud forms where rising air in the wave cools enough for moisture to condense. It fades again, where the air sinks and warms on the other side of the wave. This means a lenticular cloud can seem almost still, even though the air within it is moving steadily. Pilots pay attention to these clouds because they can mark strong wave motion and turbulence near mountains. From the ground, they often look peaceful and polished, with clean edges and graceful curves. A lenticular cloud is a visible crest in an invisible river of air. Its stillness is an illusion created by constant renewal. Kelvin-Helmholtz clouds form when layers of air slide past each other at different speeds. Their famous curling wave shapes can look like a row of breaking ocean waves painted across the sky. The pattern appears when a faster layer of air moves over a slower one, creating rolling motion along the boundary between them. These clouds are usually short-lived because the delicate curls quickly mix and lose their shape. They can form at different heights when the right combination of moisture, wind, and stability is present. Although they may look artistic, they are a physical sign of wind shear, which means a change in wind speed or direction with height. Kelvin-Helmholtz clouds reveal that the atmosphere can behave like a fluid, forming waves in air just as water does in the sea. Long rows known as cloud streets are shaped by organized wind patterns. They often form when cold air moves over a warmer surface, such as an ocean or a large lake. The surface warms the air from below, creating rising and sinking rolls that line up with the wind. Clouds form in the rising parts of these rolls, while clearer lanes appear where air sinks. From above, cloud streets can look like parallel white tracks stretching across the landscape or sea. From the ground, they may appear as repeated bands of low cumulus or stratocumulus. Their order is not accidental. It comes from the atmosphere arranging small motions into long, steady patterns. Cloud streets show that even a breezy sky can have quiet organization. Their repeated spacing makes air movement visible across great distances. Marine layer clouds often form when cool, moist ocean air lies beneath warmer air above. This arrangement can trap the lower air near the surface, creating a stable layer where low clouds or fog spread along coasts. The ocean supplies moisture, while the cool surface helps the air reach condensation. In many coastal regions, these clouds are most common during morning hours and may thin as land warms during the day. Hills and cliffs can shape where the cloud layer moves, sometimes letting it flow inland through valleys. Marine layer clouds can make the coast feel muted and calm, with soft light and softened horizons. They are a reminder that ocean temperature, air stability, and land shape can work together to create a familiar grey sky. Their edges often follow coastlines in slow, graceful forms. Trade wind cumulus clouds are small. Fair weather clouds, common over tropical oceans. They form in the steady flow of trade winds. where warm ocean water supplies moisture and gentle rising motion. These clouds are usually low, scattered, and bright, with clear blue spaces between them. Their modest size shows that the air is moist enough to form clouds, but stable enough to limit strong upward growth. They play an important role in tropical climate because they reflect sunlight and help regulate the exchange of heat and moisture between ocean and atmosphere. Seen from a ship or island shore, trade cumulus clouds can seem almost endless, repeating across the horizon in soft patterns. They are among the most peaceful signs of Earth's large-scale wind belts. Each small cloud marks a pocket of rising warm air. Narrow contrails can form behind aircraft in cold, moist upper air. The word comes from condensation trails. Aircraft engines release water vapor, and the air behind a plane can cool quickly enough for that vapor to freeze into tiny ice crystals. Some contrails fade within seconds if the surrounding air is dry. Others spread and linger when the upper air is moist, gradually becoming wider streaks of ice cloud. Contrails are human-made, but they follow the same basic rules as natural cloud formation: water vapor, particles, temperature, and humidity. Their presence can reveal conditions high above the ground, far above most familiar low clouds. A thin line behind a plane is a small cloud drawn by motion through cold air. Its lifetime depends on the invisible moisture surrounding it. Asperitas clouds have a rough, wave-like underside that can make the sky look textured and folded. The name refers to a cloud feature officially recognized in modern cloud classification. These clouds are not a separate basic cloud genus, but a supplementary feature that can appear with certain cloud layers, especially stratocumulus or altocumulus. Their uneven lower surface may be shaped by wave motion, turbulence, and changes in light beneath the cloud base. The result can look dramatic, but the structure often passes without severe weather at the observer's location. Asperitas clouds are a good example of how cloud classification still changes when observers and scientists agree that a recurring sky pattern deserves a clear name. They show that the familiar sky can still offer forms that feel newly noticed, even after centuries of cloud watching. Undulatus clouds form in wave-like bands or ripples across the sky. Their name comes from the idea of waves, and the pattern appears when a cloud layer is shaped by gentle atmospheric waves. Air rises and cools along the crests, helping cloud form, while sinking areas can thin or clear the cloud between bands. This can create parallel lines, soft rows, or a rippled sheet overhead. Undulatus can occur with several cloud types, including altocumulus and stratocumulus, because it describes a pattern rather than a height by itself. The clouds reveal that air can move in repeating waves, even when no wind is strongly felt at the ground. Their order can be quiet and beautiful, like fine lines drawn across a pale ceiling. The sky becomes a visible record of smooth motion moving through a moist layer. Fall streak holes can appear when droplets freeze or evaporate in a thin cloud layer. These openings are often called fall streak holes or hole punch clouds. They usually form in clouds made of supercooled liquid droplets. When ice crystals begin forming in one patch, nearby droplets can evaporate and feed the growing ice. The crystals may fall downward as a wispy streak, leaving a rounded or oval gap in the cloud sheet. Aircraft passing through a supercooled cloud layer can sometimes trigger this process by disturbing the air and encouraging ice formation. The result can look strange, but it follows ordinary cloud physics. A hole in a cloud is not empty sky appearing at random. It can be the visible trace of liquid water changing into ice and falling away from its former layer. Noctilucent clouds are extremely high clouds that shine after sunset or before sunrise. They form far above ordinary weather clouds in the upper atmosphere where temperatures can become very cold. Their name means night shining, because they are lit by the sun when the ground below is already in darkness. They often appear as thin, bluish, rippled veils near the horizon during summer at higher latitudes. These clouds are made of tiny ice crystals, forming around small particles in very dry, cold air. They are much higher than cirrus clouds and belong to a different region of the atmosphere. Noctilucent clouds are not part of everyday weather, but they reveal that even the edge of space can hold faint traces of water and light. Their glow is quiet because the sun is shining from far below the horizon. Polar stratospheric clouds form high above the poles in extremely cold stratospheric air. They are sometimes called nacreous clouds because they can show pearly colors after sunset or before sunrise. Unlike most familiar clouds, they form above the troposphere, where ordinary weather takes place. They need very low temperatures, so they are mainly associated with polar winter conditions. Their beauty is delicate, but they are scientifically important because chemical reactions on their particles can influence ozone in the polar stratosphere. This makes them a quiet example of how cloud particles can affect the atmosphere beyond weather and scenery. When seen from the ground, they may glow with soft bands of color against a darkening sky. Their presence points to a cold, high region most clouds never reach. Few cloud types seem so still and distant. Inside a typical liquid cloud, droplets are usually far smaller than raindrops. A droplet inside a typical liquid cloud may be only a few micrometers across, so small that it can drift with the surrounding air instead of falling quickly. A raindrop is much larger, often hundreds of times wider, and it falls because gravity can overcome the air resistance holding tiny droplets aloft. This difference helps explain why a cloud can look full of water without immediately releasing rain. The droplets are real, but they are spread out through a large volume and move with small currents inside the cloud. Many will evaporate before they ever become large enough to fall. A cloud is therefore a collection of beginnings, where water has gathered into visible form, but has not always completed the long, quiet path toward precipitation. Inside warm clouds, droplets grow by bumping into each other and joining together. In a warm cloud, tiny droplets move with air currents, drifting upward, downward, and sideways. Some droplets are slightly larger than others, so they fall a little faster. As they move, they can collide with smaller droplets and merge into bigger ones. This process is called collision and coalescence. When droplets become large enough, the air can no longer hold them up easily, and they begin to fall as rain. Many droplets never reach that size and simply evaporate back into invisible vapor. Rain is therefore not just water leaving a cloud. It is the result of countless small meetings between droplets inside a moving, changing body of air. Ice crystals help many clouds produce rain and snow. In colder parts of a cloud, water vapor can turn into ice, and tiny droplets may freeze. Ice crystals often grow more easily than liquid droplets in very cold air, because water vapor can deposit directly onto their surfaces. As the crystals grow, they may fall through the cloud and collect more ice or melt into raindrops before reaching the ground. This process is especially important in middle and high clouds, where temperatures are low enough for ice to form, a snowflake, a raindrop, and a cold grey cloud can all be linked by the same hidden growth process. The sky often begins its falling water as ice, even when the ground receives rain. Supercooled water can remain liquid inside clouds, even below freezing. In cold parts of the atmosphere, tiny droplets do not always turn to ice as soon as the temperature drops below 0 degrees Celsius or 32 degrees Fahrenheit. If there is no suitable ice-forming particle nearby, a droplet can stay liquid in a delicate, chilled state. These supercooled droplets are common in some clouds and are important for precipitation formation. When they touch an ice crystal or certain surfaces, they may freeze quickly. This process helps snow crystals grow and can create icy coatings on aircraft, which is why pilots and weather forecasters pay close attention to it. Supercooled cloud water shows that freezing is not only about temperature. It depends on the tiny surfaces and particles that water meets in the air. Mixed phase clouds contain both liquid droplets and ice crystals at the same time. These clouds are common in cold regions of the atmosphere where temperatures are below freezing, but not all water has frozen. The liquid droplets may be supercooled, while ice crystals grow nearby. Because vapor tends to move more readily onto ice than onto liquid water under these conditions, ice particles can grow while droplets shrink. This interaction can help precipitation develop. Mixed phase clouds are especially important in many mid-latitude and polar weather systems. They are challenging to represent in weather and climate models because they depend on small particles, temperature, and turbulent motion. A mixed phase cloud is a quiet meeting place of two states of water. Liquid and solid exist side by side, shaping the cloud's life from within. Snow crystals grow inside clouds when water vapor attaches to ice. In cold cloud regions, a small ice particle can become the starting point for a crystal. Water vapor deposits directly onto it, building delicate arms, plates, columns, or branching shapes depending on temperature and humidity. The crystal may pass through different layers as it falls, so its final shape can record a quiet journey through changing air. Snowflakes often contain many crystals joined together, not just one perfect star. Their forms are famous for variety, but the basic process is orderly. Vapor becomes ice, and ice grows along patterns set by the structure of water molecules. A snow crystal is a cloud particle that has become visible in greater detail. It carries the cold geometry of the cloud down toward the ground. Graupel forms when snowflakes collect supercooled droplets and become soft ice pellets. As a snow crystal falls through a cloud, liquid droplets below freezing can freeze onto its surface. This coating process is called riming. Instead of keeping its delicate branching shape, the snowflake becomes rounded, opaque, and more pellet-like. Graupel is softer and more crumbly than hail, and it usually forms on a smaller scale. It can fall during wintry showers, sometimes bouncing lightly when it reaches the ground. In the cloud, graupel can be an important step in the growth of larger ice particles because its shape and motion affect how it collides with other particles. Graupel reminds us that cloud ice is not only snowflake or hailstone. There are many gentle middle forms shaped by how frozen and liquid water meet. Hailstones grow inside strong cumulonimbus clouds where rising air can lift ice repeatedly. A small ice particle may begin high in the cloud, then move through regions containing supercooled droplets. When those droplets strike the ice, they freeze onto it, adding a new layer. Powerful updrafts can carry the growing stone upward again, allowing more layers to form before it finally becomes too heavy and falls. Not every tall cloud produces hail, because the right combination of strong rising air, liquid water, and cold levels is needed. The layered structure of a hailstone can sometimes show its repeated travel through the cloud. Hail is a dramatic form of precipitation, but its growth is still based on the same quiet ingredients: water, ice, motion, and temperature. Inside the cloud, those ingredients meet again and again. Sometimes precipitation falls from a cloud but evaporates before reaching the ground. This is called virga. It often appears as pale streaks or wispy curtains hanging beneath a cloud base. The drops or ice crystals begin their descent normally, but they pass through a layer of dry air below the cloud. As they fall, they evaporate or sublimate, changing back into invisible vapor. This is common in dry regions, where clouds may seem to release rain that never touches the land. Virga can make the lower edge of a cloud look soft, trailing, and blurred. It is a reminder that precipitation has a journey, and not every drop completes it. Sometimes a cloud gives water back to the air before the ground ever feels it. In that quiet exchange, falling water returns to sky. Visible rain shafts are columns or curtains of precipitation falling from clouds. From a distance, they may look like grey streaks reaching down from a darker cloud base. Their shape depends on how much rain or snow is falling, how strong the wind is, and whether some of the precipitation evaporates before reaching the surface. In sunlight, a rain shaft may appear pale and silvery. Under a thick cloud, it may look blue-grey or shadowed. Rain shafts help observers see where precipitation is concentrated, because not every part of a cloud releases water evenly. One side of a cloud may be dry, while another sends a soft curtain downward. A rain shaft is the cloud's water made visible in motion. It connects the floating shape overhead with the ground, the sea, or the forest below. Fine drizzle comes from very small liquid drops falling from low clouds. It is most often linked with stratus or stratocumulus clouds, where gentle upward motions and shallow cloud layers allow droplets to grow only modestly. Drizzle drops are smaller than ordinary raindrops, so they fall slowly and can seem to float through the air. They may dampen surfaces quietly without forming the clear splashes of heavier rain. In coastal and cool regions, drizzle can be common when low clouds remain moist, but do not have the depth or strong motion needed for larger raindrops. It shows that precipitation does not always arrive in strong showers or steady rain. Sometimes a cloud releases water in the smallest falling form, soft enough to blur distant trees and leave a fine sheen on leaves, stones, and roofs. Freezing rain begins as snow or ice high in a cloud and becomes liquid before freezing on contact. The process usually needs a warm layer of air above the ground, with a shallow layer of sub-freezing air near the surface. Snowflakes fall from the cloud and melt into raindrops as they pass through the warmer layer. Near the ground, the drops become supercooled, remaining liquid even though their temperature is below freezing. When they touch roads, branches, wires, or other cold surfaces, they freeze into a smooth coating of ice. The cloud's roll is the beginning of a layered journey through the atmosphere. Freezing rain shows how the same falling particle can change form more than once before reaching the surface. Its final state depends on the hidden temperature layers beneath the cloud. Sleet forms when raindrops freeze into small ice pellets before reaching the ground. Like freezing rain, it begins with layered temperatures in the atmosphere. Snow or ice falls from a cloud, melts in a warm layer, and then enters a deeper layer of sub-freezing air below. If that cold lower layer is thick enough, the drops freeze again while still falling. By the time they reach the ground, they have become small pellets that may bounce lightly on hard surfaces. Sleet is sometimes confused with hail, but its path is different. Hail grows within strong storm clouds, while sleet forms through melting and refreezing during descent. A sleet pellet is a tiny record of vertical structure. It tells us that the air between cloud and ground was arranged in layers of warmth and cold. Rime ice forms when supercooled cloud droplets freeze onto cold surfaces. This often happens on mountains, towers, trees, or aircraft that pass through freezing fog or cloud. The droplets are liquid while suspended in the air, but they freeze quickly when they strike a surface below freezing. The result can be a rough white coating that grows into the wind, sometimes creating feathery or crusted shapes. Rime is different from frost, which usually forms when water vapor deposits directly as ice on a cold surface. Rime needs cloud or fog droplets. On high ridges, it can show which way moist wind has been blowing for hours. It is cloud water made solid on contact, turning invisible airflow and suspended droplets into a textured layer that clings to branches, rocks, and exposed structures. Downdrafts can form when falling precipitation cools the air beneath a cloud. As raindrops or ice particles fall into drier air, some of their water evaporates or sublimates. This change takes energy from the surrounding air, cooling it. Cooler air is denser, so it can begin sinking toward the ground. In large clouds, downdrafts may become organized regions of descending air beside rising currents. They are part of the cloud's internal circulation, helping move moisture, heat, and particles through different levels. Downdrafts can spread cooler air outward when they reach the surface, sometimes shaping new cloud boundaries nearby. Even in less dramatic weather, the idea is gentle and clear. Falling water can cool the air it passes through. A cloud may therefore create not only rain, but a quiet downward movement beneath itself. Morning fog often forms when the ground cools overnight under clear skies. During the night, the surface loses heat, and the air resting near it can cool as well. If this air contains enough moisture, it may reach the temperature where water vapor condenses into tiny droplets. Calm winds help the droplets remain near the ground instead of mixing away. This kind of fog is called radiation fog because it is linked to heat radiating away from the surface. It is common in valleys, fields, and low places where cool air gathers. After sunrise, warming can evaporate the droplets and return the fog to invisible vapor. Morning fog shows how a cloud can appear from the day's quiet temperature cycle, forming close to grass, roads, rivers, and rooftops. Valley fog collects in low places because cool air naturally drains downhill. After sunset, slopes and high ground can cool quickly, and the denser air near them begins to slide into valleys. If the air is moist enough, fog may form and settle in the lower landscape, while nearby hills remain clear. From above, valley fog can look like a pale river or lake of cloud, filling the land's lowest spaces. The fog may persist after sunrise if the valley stays shaded, or if the air remains trapped under an inversion. Its shape is guided by topography, following river corridors, basins, and gentle hollows. Valley fog is a quiet example of land and atmosphere fitting together. The cloud does not simply cover the ground, it takes the shape of the place that holds it. Advection fog forms when moist air moves over a cooler surface. As the moving air touches cooler land or water, it loses heat from below. If it cools enough, water vapor condenses into tiny droplets, creating fog. This kind of fog is common along coasts, where mild, moist air can pass over colder ocean water. It can also occur when warm air moves over snow-covered ground. Unlike radiation fog, which often forms in calm conditions overnight, advection fog depends on horizontal movement of air. Wind can help bring in the moisture and keep the fog supplied, though strong mixing may lift or break it. Advection fog shows that a cloud near the ground can be carried into place. It is a meeting between moving air and a surface cool enough to reveal its moisture. Halos appear when sunlight or moonlight passes through ice crystals high in the sky. Thin clouds such as cirrostratus can contain countless small crystals with simple geometric shapes. As light enters and leaves these crystals, it bends in predictable ways, often forming a pale ring around the sun or moon. The most familiar halo is a wide circle, though other arcs and bright spots can appear when the crystals are aligned in certain patterns. These displays are optical effects, not objects placed in the sky. They are signs that thin, icy cloud is spread overhead, sometimes before a change in weather. A halo turns hidden ice into visible geometry. It lets the sky draw a quiet circle of light around the source that illuminates it. The effect depends on crystal shape, angle, and height. Iridescence happens when tiny droplets or ice crystals separate sunlight into soft colors. It is most often seen near the sun, along thin cloud edges where the particles are small and fairly even in size. The light waves bend and overlap as they pass around the droplets, creating pastel patches of pink, green, blue, or violet. The colors are usually delicate, not as bold as a rainbow, and they may shift as the cloud changes shape. Iridescence is easiest to notice when the sun is partly blocked, because looking near bright sunlight can be uncomfortable and unsafe. The effect shows how small cloud particles can interact with light in precise ways. A plain white cloud can briefly reveal a hidden shimmer of color. Its softness comes from physics working at a very small scale. At sunrise and sunset, clouds can become vivid by catching low-angle sunlight. Near sunrise and sunset, sunlight travels through more of the atmosphere before it reaches the clouds. Much of the shorter blue light is scattered away along the path, leaving more reds, oranges, and pinks to illuminate cloud bases and edges. High clouds are often especially colorful because they can remain sunlit after the ground is already in shadow. The brightness and color depend on cloud height, thickness, and the clarity of the air between the sun and the cloud. A plain cloud at midday can become richly colored at day's end without changing its water or ice. The difference comes from the path of light. Sunset clouds reveal that the sky's color is not fixed, but shaped by angle, distance, and scattering. Crepuscular rays appear when clouds block sunlight in some places and let it pass in others. These rays often seem to fan outward from the sun, especially when the sun is low and partly hidden behind cloud. The beams are made visible by tiny particles and droplets in the air, scattering the light toward the observer. The dark spaces between them are cloud shadows stretching through the atmosphere. Although the rays look as if they spread apart, they are mostly parallel. Perspective makes them appear to widen, like railroad tracks seeming to meet in the distance. Clouds are essential to the effect because they create the openings and shadows. Crepuscular rays turn cloud edges into a quiet pattern of light and shade, making the air itself seem softly illuminated. A cloud bow is a pale cousin of a rainbow formed by tiny cloud or fog droplets. It appears when sunlight is reflected and refracted inside droplets, but the droplets are much smaller than typical raindrops. Because the droplets are so small, the colors overlap and blur, often leaving a broad white or faintly tinted arc. Cloud bows are sometimes seen from mountains, aircraft, or within fog when the sun is behind the observer. They are not as bright or sharply colored as rainbows, but they follow related light behavior. Their softness comes from the size of the droplets, making the color bands less distinct. A cloud bow shows how even the gentlest mist can bend light into a shape. It is a quiet optical trace of sunlight passing through floating water. Glories appear as colored rings around the shadow of an observer cast onto cloud or fog. They are often seen from aircraft, mountain ridges, or high places when the sun is behind the viewer and cloud droplets lie ahead. The effect is linked to light interacting with tiny droplets and returning toward the observer in a complex pattern. A glory can surround the shadow of a plane or a person, though each observer sees their own version from their own position. The rings are usually smaller and more concentrated than a rainbow. Clouds and fog provide the droplets that make the effect visible. A glory is a personal-looking sky display created by shared physics. It reminds us that some cloud colors depend not only on the cloud, but on exactly where the viewer stands. The Brocken spectre is a large shadow cast onto cloud or fog from a high place. It is named after the Brocken, a mountain in Germany where the effect was famously observed. When a person stands with the sun behind them and fog or cloud below or ahead, their shadow may appear stretched and enlarged on the mist. Perspective and the uneven cloud surface can make the shadow seem much larger than the person casting it. A glory may sometimes appear around the shadow's head, adding colored rings. The effect can look mysterious, but it is a simple meeting of sunlight, droplets, and viewpoint. The cloud acts like a screen suspended in the air. It receives the shadow and turns an ordinary human outline into a quiet atmospheric image. A passing cloud can cast a shadow that cools the surface below. When a cloud passes in front of the sun, it blocks some of the incoming sunlight that would otherwise warm land, water, buildings, and plants. A thin cloud may soften the light only slightly, while a thick cloud can make the air feel noticeably cooler. Over large areas, cloud cover can influence daily temperatures by reducing daytime heating. At night, clouds can have a different effect, helping trap some heat near the surface and slowing how quickly the ground cools. This balance is one reason clouds matter so much to climate and weather. They are not only decorations in the sky, they help shape how energy moves around Earth. Moving cloud shadows can travel across land and sea faster than the clouds appear to move. A cloud high above the ground casts a shadow along the path of sunlight. Because the sun's angle stretches that shadow, its shape and speed across the surface can differ from the cloud's visible motion overhead. On windy days, patches of shade may sweep across hills, fields, lakes, or ocean waves in broad moving patterns. From mountains or aircraft, these shadows can reveal the height and spacing of cloud layers. They can also change the surface temperature for a short time as sunlight is briefly reduced. A cloud shadow is not separate from the cloud, but it belongs to the ground below. It is the cloud's temporary mark on the landscape. Lake effect clouds form when cold air moves over relatively warmer lake water. The lake adds heat and moisture to the lower air, making it more likely to rise. As that air travels downwind, it can cool and condense into bands of cloud. In cold seasons, these clouds may produce narrow zones of snow on the far shore, while nearby, places outside the band receive much less. The strength of lake effect clouds depends on water temperature, air temperature, wind direction, and how long the air travels over the water. Large lakes are especially effective because they give air more time to gather moisture. A lake effect cloud band is a visible path of exchange between water and winter air. It shows how a surface far below can shape weather far downwind from shore. Forests can help supply moisture that later becomes cloud. Trees draw water from the ground and release some of it through tiny openings in their leaves, a process called transpiration. This water enters the air as vapor, joining moisture from soil, rivers, lakes, and oceans. In warm regions with large forests, the added moisture can contribute to cloud formation when air rises and cools. Forests can influence local temperatures and air movement, which may affect when and where clouds appear. This does not mean every cloud over a forest comes directly from the trees below, because the atmosphere mixes air from many sources. But forests are active participants in the water cycle. Their leaves quietly pass water upward, helping connect roots, air, and cloud in one living exchange above the land. Pyrocumulus clouds form when intense heat drives air rapidly upward. Large wildfires, volcanic eruptions, or other powerful heat sources can warm the air above them so strongly that it rises like a column. If that rising air contains enough moisture or reaches levels where condensation can occur, a cloud may build above the heat source. The cloud can look like a growing cumulus tower, but its lift comes from fire or volcanic heat rather than ordinary surface warming alone. Ash, smoke, and tiny particles can become part of the cloud environment. Some very large pyrocumulus clouds can grow into pyrocumulonimbus, reaching heights where they influence weather locally. The process shows how Earth's surface can send sudden energy into the atmosphere, turning heat, particles, and moisture into a visible cloud above. Over cities, clouds can be influenced by heat and particles from urban areas. Buildings, roads, and paved surfaces often warm strongly during the day, creating an urban heat island compared with nearby countryside. This warmth can encourage rising air. Cities can add aerosols, which are tiny particles that may serve as surfaces for cloud droplets. The effect is complex and depends on wind, humidity, geography, and the type of particles present. In some situations, urban areas may influence cloud formation or precipitation patterns downwind. This does not mean a city simply makes clouds appear on command. It means the built environment can become one more part of the lower atmosphere. A cloud passing over a city may be shaped not only by natural weather, but also by the surfaces and particles below. Inside large storm clouds, droplets and ice particles can help separate electric charge. In tall clouds with strong rising and sinking motion, ice crystals, graupel, and supercooled droplets collide many times. These collisions can help separate electric charge, with different parts of the cloud becoming more positive or more negative. The exact details are complex, but the general result is that a cloud can become electrically organized. When the difference in charge grows large enough, lightning may occur within the cloud, between clouds, or between cloud and ground. The process is powerful, yet it begins with small particles moving through cold, wet air. A towering cloud is not only a place of water and ice, it can also become a quiet generator, building charge through countless tiny meetings hidden inside its deep grey walls. Lightning often travels through clouds before it reaches the ground. Many flashes never leave the cloud at all, because the electrical difference is strongest between regions inside the cloud itself. These cloud-to-cloud or intra-cloud flashes can light up the sky from within, making a large cloud glow for a moment like a lantern. The visible flash is only part of the process, because a channel of ionized air forms first, allowing electric charge to move. Lightning is brief, but it reveals how much structure can exist inside a cloud. Different layers, particles, and currents help build the conditions for a flash. Even when seen from far away, the light shows that a cloud can hold hidden order, with water, ice, wind, and electricity arranged through height and distance. Thunder is the sound of air rapidly expanding around lightning. When a lightning channel heats the air along its path, that air expands suddenly and sends out a pressure wave. By the time the sound reaches the listener, it may rumble softly because different parts of the lightning channel are at different distances. Hills, buildings, forests, and layers of air can reflect and bend the sound, spreading it into a long, low roll. Thunder belongs to clouds because it is created by electrical activity inside or near them. It is not the cloud itself making a voice, but the air responding to a sudden flash of energy. In calmer terms, thunder is the atmosphere carrying a message from a bright, brief event hidden in a tall cloud. An overshooting top forms when a storm cloud briefly punches above its usual ceiling. In a powerful cumulonimbus cloud, the updraft can be strong enough to push the cloud top above the flat anvil and into the lower stratosphere for a short time. This creates a rounded dome or bubble rising above the smoother upper surface. The feature shows that air inside the cloud is still moving upward with great force, even near the top of ordinary weather. Overshooting tops are important to meteorologists because they can signal especially strong storms. From a distance, the shape may look small compared with the whole cloud, but it marks intense vertical motion. It is a cloud leaving a temporary fingerprint on the boundary between the lower atmosphere and the quieter air above. A wall cloud forms beneath some strong storm clouds where air is drawn upward. It appears as a lowering from the base of a cumulonimbus cloud, often under the rain-free part of the storm. Moist air rising into the storm cools and condenses at a lower height than the surrounding cloud base, making the lowering visible. Wall clouds are important because they can show where the storm's internal air motion is focused. Some rotate, though not every wall cloud does. Their shape can change as air is pulled in, lifted, and mixed with rain-cooled air nearby. For a sleep-friendly view, the important fact is structural rather than dramatic. A wall cloud is a visible sign that the bottom of a large cloud is not flat everywhere. It can dip where rising air is strongest. Shelf clouds are long, low cloud formations shaped by cool air spreading outward. They often form along the leading edge of outflow from a thunderstorm, where cooled air from falling precipitation moves away from the storm and lifts warmer, moist air ahead of it. As that warmer air rises, it condenses into a broad horizontal cloud with a smooth or layered appearance. A shelf cloud is attached to the parent storm, unlike some roll clouds that detach and travel separately. Its shape can look like a curved ledge across the sky, marking the boundary between two moving air masses. The cloud itself is a sign of airlifting along a shallow front created by the storm. It shows how falling rain can reshape the air near the ground and create a new cloud edge, Roll clouds are long, tube-shaped clouds that can appear detached from other cloud systems. They form when air near a boundary begins to rotate horizontally, often along a line where cooler air moves beneath warmer, moist air. As the rotating air rises on one side of the tube, moisture can condense into cloud. As it sinks on the other side, parts may evaporate. This gives the cloud a long, rounded shape that can seem to roll across the sky. Roll clouds are a type of Arcus cloud, but unlike shelf clouds, they are usually separated from the main storm cloud. They can stretch for great distances when conditions are right. Their calm visual shape comes from organized motion, with air turning slowly along an invisible horizontal axis. Sea breezes can help clouds form along coastlines. During the day, land often warms faster than nearby water. The warmer air over land rises, and cooler air from the sea moves inland to replace it. Where this sea breeze meets warmer inland air, the air can be lifted enough for moisture to condense into clouds. In some regions, a line of cumulus clouds marks the boundary as it slowly moves away from the coast. The clouds may appear in the afternoon, following the daily heating of land and the steady coolness of the water. Sea breeze clouds show how local geography can shape the sky on a familiar rhythm. The shoreline becomes more than a boundary between land and ocean. It becomes a place where air moves, rises, and briefly turns white. Monsoon clouds grow from seasonal shifts in wind and moisture. A monsoon is not simply heavy rain. It is a broad seasonal change in atmospheric circulation. In many regions, warm land helps draw moist air from nearby oceans during part of the year. As this moisture moves inland and rises, deep clouds can form, bringing widespread rain that supports rivers, farms, wetlands, and forests. The exact timing and strength vary by region, but the cloud story is rooted in large-scale movement of heat and moisture. Monsoon clouds often build day after day during the wet season, linking ocean evaporation with life far inland. They show how clouds can belong to a seasonal rhythm much larger than a single storm. A sky filled with monsoon cloud carries the memory of warm seas and heated land. In hurricanes, clouds organize around a rotating center over warm ocean water. These storms form only under specific conditions, including warm seas, moist air, and favorable winds aloft. Their clouds are not random. They arrange into spiral rain bands and a central region of intense cloud surrounding the eye. The warm ocean supplies water vapor and heat, while rising air condenses into deep clouds that release energy and help the storm maintain its circulation. From satellite view, the cloud pattern can look like a vast white spiral across the sea. The subject can be powerful, but the cloud structure is a lesson in organization. Millions of droplets and ice crystals align within rotating air. A hurricane's cloud shield shows how heat from the ocean can be transformed into one of the atmosphere's largest patterns. The eye of a strong tropical cyclone is often clear because air sinks near the center. Around the eye, towering clouds rise in the eye wall, where warm, moist air ascends and precipitation is concentrated. Inside the eye itself, air generally descends, warming as it sinks. This warming lowers relative humidity and can reduce cloud formation, sometimes allowing blue sky or stars to appear overhead. The eye is not a separate object, but a calm-looking region created by the storm's rotating circulation. Its size and clarity can change as the storm changes. Seen from above, the eye can make the cloud system look almost like a ring around an opening. It shows that clouds form where air rises, and they can thin where air sinks, even within the same vast storm. By reflecting sunlight back to space, clouds can cool Earth. Bright cloud tops send a portion of incoming solar energy away before it can warm the surface. Low, thick clouds are especially good at this because they are often bright and cover large areas. This reflective effect is called albedo, and it helps explain why a cloudy day may feel cooler than a clear one. The amount of cooling depends on cloud height, thickness, droplet size, and coverage. Clouds over dark oceans can have a strong influence because they replace a surface that would otherwise absorb much more sunlight. This cooling role is one side of the cloud-climate balance. A cloud can act like a pale shield, gently reducing the sunlight that reaches the world below. Even a thin layer can soften the day's warmth by slowing the escape of heat into space. Clouds can warm Earth. The surface releases energy upward as infrared radiation, especially after it has been warmed by sunlight. Clouds absorb some of that outgoing energy and emit part of it back downward. High, thin clouds can be especially important in this warming effect because they are cold and radiate less energy to space than the warmer surface below. At night, a cloudy sky often helps keep temperatures milder than a clear sky because heat escapes more slowly. This warming role does not cancel the reflective cooling role in a simple way. Different clouds have different effects. A cloud is part mirror and part blanket, depending on where it forms and what it is made of. Its height can change its influence on Earth's energy balance. Feedback involving clouds is one of the important questions in climate science. As Earth warms, cloud patterns may change in height, thickness, location, and amount. Those changes can either increase warming or reduce some of it, depending on the type of cloud and where it forms. Low clouds tend to reflect sunlight strongly, while high clouds often have a stronger warming effect. Small shifts in cloud cover over oceans can matter because oceans occupy so much of the planet's surface. Scientists study clouds with satellites, weather stations, aircraft, and computer models. But cloud behavior remains difficult because clouds form from tiny processes inside vast moving systems. The basic idea is simple. Even if the details are complex, clouds help decide how much energy Earth keeps and how much it returns to space. In cloud forests, life depends on frequent contact with low clouds and fog. These forests grow in mountain regions where moist air often condenses at the same height as the trees. Instead of receiving water only from rain, the vegetation can collect tiny droplets from passing cloud. Leaves, mosses, and branches intercept the moisture, which may drip down to the soil. This steady cloud contact helps support rich communities of plants, lichens, insects, birds, and amphibians. The air is often cool, damp, and softly shaded, with clouds moving through the forest rather than above it. Cloud forests show that clouds are not distant from life on the ground. In some places, they enter the branches and become part of the habitat. The forest and the cloud share the same space, joined by mist and leaf. Tiny living organisms can travel through the atmosphere inside or alongside clouds. Bacteria, fungal spores, pollen, and other biological particles can be lifted by wind and become part of the air where clouds form. Some of these particles may act as surfaces for water droplets or ice crystals, though their importance varies with location and conditions. Scientists have found that the atmosphere is not empty above the ground. It contains small traces of life moving with dust, moisture, and air currents. These organisms do not make clouds alive in the usual sense, but they show how connected the lower atmosphere is with oceans, soils, forests, and fields. A cloud can contain water, minerals, salts, soot, and tiny biological fragments all at once. Its whiteness hides a quiet mixture gathered from many parts of Earth. Dust from deserts can help ice form inside clouds far away. Strong winds can lift fine mineral particles from dry landscapes and carry them across regions or even oceans. Some of these particles can serve as ice nuclei, giving supercooled water a surface on which to freeze. This matters because ice formation can influence whether a cloud produces snow or rain. Desert dust can also affect how much sunlight clouds reflect and how droplets form around particles. The journey may be long, with dust from one continent entering cloud systems over another. The idea is calm but remarkable. A tiny grain lifted from dry ground can later help shape a cloud in moist air. Clouds are not only local events. They can carry signs of distant landscapes within their droplets and crystals. Sea salt particles help many ocean clouds begin as droplets. Waves breaking at the surface throw tiny bits of salty spray into the air. As the water in the spray evaporates, small salt particles can remain suspended. These particles attract water easily, making them effective cloud condensation nuclei. Over wide ocean areas, they help water vapor gather into droplets when moist air rises and cools. Marine clouds often form in air that has been shaped by this steady exchange between sea and sky. The salt inside a cloud droplet is tiny, but it can influence how readily the droplet forms and grows. Ocean clouds therefore carry a trace of the water below them, not only as vapor, but as fine particles lifted from breaking waves. Each low cloud over the sea begins partly with the sea's own spray. Volcanic eruptions can send particles high into the atmosphere that affect clouds and light. Ash and sulfur-rich gases can rise with hot plumes, and some material may reach levels above ordinary weather clouds. In the stratosphere, sulfur gases can form tiny sulfate particles that scatter sunlight. These particles are not the same as familiar low clouds, but they can create hazy layers and influence the color of sunrises and sunsets for a time. Near an eruption, ash and moisture can also become involved in cloud formation within the plume. Volcanic particles show how events at Earth's surface can change what floats overhead. The atmosphere can carry fine material over great distances, turning solid rock and gas into suspended particles. In this way, even a distant eruption may leave a soft visual trace in the sky. Jet streams can stretch high clouds into long, thin bands. These fast rivers of air flow high in the troposphere and often guide weather systems around the planet. When moisture is present near their level, strong winds can pull ice clouds into streaks, veils, or feathered patterns. Cirrus clouds may reveal the direction of the flow long before surface winds change. The cloud particles themselves are tiny, but the wind field shaping them can extend across continents and oceans. Jet streams do not create every high cloud, but they often sculpt the upper sky with smooth, stretched forms. A pale streak of cirrus can be a sign of motion far faster and higher than anything felt at the ground. It lets the eye glimpse one of the atmosphere's great hidden currents. Gravity waves can create repeating cloud bands in a stable layer of air. These waves are not the same as gravitational waves in space. They are atmospheric ripples caused when displaced air is pulled back toward balance by gravity and buoyancy. Mountains, storms, fronts, or strong winds can disturb the air and send waves through it. Where the wave lifts moist air, cloud may form. Where the wave lowers air, the cloud may thin or vanish. This can create evenly spaced bands, ripples, or patches across the sky. The pattern may look delicate, but it reflects organized motion over a broad area. Gravity wave clouds show that the atmosphere can ring gently after being disturbed. Moisture makes the waves visible for a while, drawing their crests as pale lines overhead. Seeding a cloud is an attempt to encourage precipitation by adding particles to clouds. The method usually targets clouds that already contain moisture and suitable conditions, rather than creating rain from clear air. In cold clouds, substances such as silver iodide may be used because they can encourage ice crystals to form. In some warm clouds, salt particles may be used to help droplets grow. The results can be difficult to measure because natural cloud behavior varies so much from place to place and from storm to storm. Cloud seeding is not a simple switch for making rain, and it cannot solve drought by itself. It is best understood as a careful attempt to influence existing cloud processes. The idea rests on a basic fact. Tiny particles can change how water gathers, freezes, and falls. Satellites help people study clouds across the whole planet. From orbit, instruments can watch cloud cover over oceans, deserts, mountains, forests, and polar regions, including places where ground observations are scarce. Visible images show sunlight reflected from cloud tops, while infrared sensors help estimate cloud top temperature and height. Other instruments can measure properties such as moisture, ice, and droplet size. Satellites make it possible to see the broad shape of storms, the spread of marine cloud decks, and the daily rhythm of tropical cloud fields. They do not replace local measurements, but they give weather science a wide view that no single observer on the ground could have. A satellite image turns Earth's cloud cover into a moving pattern, showing how small cloud particles can organize into structures larger than countries. Radar can reveal precipitation hidden inside clouds. Weather radar sends out pulses of energy and listens for signals reflected back by raindrops, snowflakes, hail, or other particles. The strength and timing of the return signal help show where precipitation is located and how far away it is. Some radar systems can estimate motion, giving clues about wind within storms. Radar does not see every cloud equally because tiny cloud droplets may be too small to reflect much energy. It is especially useful when cloud particles have grown large enough to fall or nearly fall. On a radar screen, invisible regions of rain and snow become patterned fields of information. This helps forecasters follow changing weather while it is still inside the cloud before all of it has reached the ground. A ceilometer measures the height of cloud bases from the ground. It sends a beam of light upward, often using a laser, and detects the light scattered back by droplets, ice crystals, or aerosols. By measuring how long the signal takes to return, the instrument estimates where the lower edge of a cloud begins. Cloud base height matters for aviation, weather reports, and understanding the lower atmosphere. Human observers once judged cloud bases mainly by eye, using experience and landmarks, but instruments can provide regular measurements even in dim or changing conditions. A ceilometer does not need to see the whole cloud. It only needs to find the first strong return from particles overhead. In this way, a quiet beam of light can turn the height of a grey sky into a useful number for the world below. Radio sondes help explain why clouds form at certain heights. A radio sonde is a small instrument package carried upward by a weather balloon. As it rises, it measures temperature, humidity, pressure, and often wind. These measurements create a vertical profile of the atmosphere, showing where air is moist, dry, stable, or likely to cool enough for condensation. Forecasters use this information to understand cloud layers, storm potential, fog formation, and the height of freezing levels. The balloon eventually bursts high above the ground, but the data it sends back can describe the invisible structure that shapes visible clouds. A radiosonde flight is simple in appearance, a balloon climbing into the sky. Its path reveals the layered conditions that decide whether water remains unseen or gathers into a soft white cloud overhead. On other planets, clouds can be made from materials very different from Earth's water clouds. On Earth, most familiar clouds involve water droplets or ice crystals, but other worlds have colder, hotter, or chemically different atmospheres. Venus has thick clouds rich in sulfuric acid droplets. Mars can have thin clouds of water ice and carbon dioxide ice. Giant planets such as Jupiter and Saturn contain cloud layers linked with ammonia, water, and other compounds deep in their atmospheres. These planetary clouds are shaped by the same broad ideas of temperature, pressure, condensation, and motion, even when the ingredients are unfamiliar. Looking beyond Earth shows that clouds are not only a feature of blue skies and rain, they are a general atmospheric pattern, appearing wherever vapor can gather into visible particles. At the end of this journey, the sky no longer feels empty. Even on the quietest day, water is moving through the air, changing between vapor, droplets, and ice. A soft white cloud may begin with sunlight warming the ground, wind crossing the sea, or a tiny particle lifted from dust, salt, or forest. Each shape overhead is part of a larger system, connecting ocean, land, weather, light, and life. Their beauty comes from constant change. A cloud can gather, brighten, darken, stretch, dissolve, or drift beyond sight. Yet nothing in it is truly lost. The water returns to the air, falls to the ground, freezes into crystals, or begins another journey across the world. In their slow movement, clouds show both delicacy and scale. They can shade a field, feed a river, crown a mountain, or spread across an entire ocean. As this journey comes to a close, let the image of clouds remain gentle and spacious. High wisps of ice, low blankets of fog, silver rain shafts, and quiet evening colors fading across the sky. Sleep well. Good night.